Tonight, we're going to explore one of the most overlooked mysteries in all of astronomy: the space between the stars. You've probably been told your whole life that space is empty, a vacuum, nothing. But here's what almost nobody realizes. The space between the stars is not empty. It's filled with things you can't see, things that shape the entire galaxy. There are invisible clouds stretching across hundreds of light years. There are magnetic fields threading through the darkness. There are particles moving at nearly the speed of light, tearing through what looks like nothing. And all of it, every single piece, plays a role in whether stars are born, whether planets form, and whether life like ours is even possible. What exists between the stars is far stranger and far more important than you've ever been told. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Go outside on a clear night, away from the city, away from the glow of streetlights and buildings, and look up. Really look. You'll see stars scattered across the darkness. Some bright, some faint, some clustered together in familiar patterns. The Big Dipper, Orion's Belt, the brilliant point of Sirius hanging low on the horizon. These stars grab your attention because they shine. They're points of light against a black canvas. Your eyes are drawn to them naturally. But now look at what's between those stars. Look at the gaps, the dark spaces, the enormous stretches of black sky where there's apparently nothing at all. That darkness seems total. It seems absolute. It looks like the stars are islands of light floating in an infinite ocean of nothing. And for most of human history, that's exactly what people believed. The space between the stars was considered empty, a void, a gap with no substance, no structure, no physical reality worth talking about. The stars were the things that mattered. The darkness in between was just absence, just nothing. But here's the truth. That darkness is not nothing. It's something. And understanding what fills that darkness, what actually exists in those enormous gaps between the stars, is one of the most fascinating and underappreciated stories in all of science. Because the space between the stars is not empty. It has never been empty. It contains matter. It contains energy. It contains forces that stretch across distances so vast they challenge our ability to think about them. And everything that fills that darkness plays a direct role in the story of how stars form, how they live, how they die, and how new stars and planets are born from the material left behind, including the planet you're standing on right now. But before we can understand what's out there between the stars, we need to understand just how far apart the stars actually are. Because the distances involved are staggering. They're so large that they redefine what the word empty even means. Let's start with something concrete. The nearest star to our sun is Proxima Centauri. It's about 4.24 light years away. Now, a light year is the distance that light travels in 1 year. Light moves at about 300,000 kilometers per second. That's fast enough to circle the entire Earth about 7.5 times in a single second. In 1 year, moving at that speed without stopping, light covers about 9.46 trillion kilometers. And Proxima Centauri, the closest star to us, is 4.24 of those light years away. That's roughly 40 trillion kilometers. 40 trillion. If you tried to drive that distance in a car going at highway speed, about 100 kilometers per hour, it would take you over 45 million years. 45 million years of continuous driving without stopping. That's longer than the entire time apes have existed on Earth. Longer than the time since Antarctica froze into the ice continent we know today. Just to reach the nearest star. Now think about this. If you shrank the sun down to the size of a basketball, sitting on your kitchen table, and you wanted to place a model of Proxima Centauri at the correct relative distance, you'd have to walk about 6,400 kilometers away. That's roughly the distance from New York City to London. The basketball on your table is the sun, and the nearest star is in London. Everything in between is empty space, or at least it looks empty. That's the scale we're dealing with. That's how far apart even the closest stars are, and most stars are much farther apart than that. Within our galaxy, the Milky Way, the average distance between stars in our neighborhood is roughly 4 to 5 light years. In denser regions near the galactic center, stars might be separated by only a fraction of a light year. In the outskirts of the galaxy, they can be separated by 10 or 20 light years or more. But the point remains the same everywhere. The space between the stars is enormous, incomprehensibly, overwhelmingly enormous. And when you look up at the night sky and see those dark gaps between the stars, you're looking at distances measured in trillions of kilometers. Regions of space so vast that even light, the fastest thing in the universe, needs years to cross them. So when someone tells you that space is empty, you can understand why they might think that. If you could somehow fly a spaceship into the region between two stars, you wouldn't see anything around you. No walls, no objects drifting by, no landmarks, just blackness in every direction with distant points of light that barely seem to get closer, no matter how fast you travel. The emptiness would be overwhelming. It would feel like the most absolute nothingness you could ever experience. But that feeling would be wrong, because the space you're flying through is not truly empty. It contains matter, incredibly thin, incredibly sparse, almost impossibly diluted, but real physical matter. And understanding just how thin this matter is requires us to think about density in a way most people never have. Let's talk about the air you're breathing right now. You don't think about air very often because you can't see it. It seems like nothing. But air is actually made of molecules, mostly nitrogen and oxygen, flying around at high speeds, bouncing off each other and off your skin and off every surface in the room. At sea level on Earth, every cubic centimeter of air, a volume about the size of a sugar cube, contains roughly 2.5 times 10 to the 19th molecules. That's about 25 billion molecules in a space the size of a sugar cube. Now, air seems thin to us. We move through it easily. It's transparent. But compared to the space between the stars, the air you're breathing right now is unbelievably, absurdly dense. In the space between the stars, in the vast dark regions separating one sun from another, the average density of matter is roughly 1 atom per cubic centimeter. Not 1 billion, not 1 million, not 1,000. One. A single lonely atom of hydrogen, floating in a volume the size of a sugar cube. Compare that to the air on Earth. Earth's atmosphere has about 25 quintillion molecules per cubic centimeter. Interstellar space has 1. The difference in density between the air in this room and the gas between the stars is a factor of about 25 billion. That's a number so large that no everyday comparison can capture it adequately. Interstellar space is not just emptier than air, it's emptier than the best vacuum chambers we've ever built on Earth. The most advanced vacuum technology humans have created can pump a chamber down to a few hundred molecules per cubic centimeter. Interstellar space is still hundreds of times emptier than that. It's emptier than anything we can create artificially. So when scientists say that interstellar space is a near-perfect vacuum, they're not exaggerating. By any standard that makes sense in everyday human experience, the space between the stars is empty. Devastatingly, overwhelmingly, almost perfectly empty. It's the kind of emptiness that makes your brain want to give up trying to imagine it. And yet, despite all of that, despite the almost perfect vacuum, the space between the stars is not empty. It contains matter, it contains structure, it contains physical processes that are happening right now, shaping the galaxy in real time. And the reason that matters, the reason scientists care about 1 atom per cubic centimeter, is scale. Because when you spread 1 atom per cubic centimeter across light years and light years and light years of space, across trillions upon trillions of cubic kilometers, those individual atoms add up. They add up to clouds of gas that outweigh entire star systems. They add up to structures that span hundreds of light years. They add up to the raw material from which new stars and planets are born. The thinness of interstellar matter is real, but the volume it fills is so incomprehensibly large that the total amount of material between the stars is enormous. Let me give you a sense of this. In our galaxy, the Milky Way, the total mass of all the gas and dust floating between the stars, all that incredibly sparse material spread across the galaxy's 100,000 light-year diameter, adds up to roughly 10 to 15% of the total mass of all the stars in the galaxy combined. The Milky Way contains somewhere between 100 billion and 400 billion stars, and the material between those stars amounts to 10 to 15% of all that stellar mass. That's billions of times the mass of our sun, just floating in what looks like empty space. It's not concentrated, it's not dense. You could fly through it for billions of kilometers and never notice it's there. But it's there, and it has always been there. The story of how we figured this out is one of the great detective stories in astronomy. Because for centuries, astronomers genuinely believed that the space between the stars was a perfect vacuum. The stars themselves were fascinating. They had colours, brightnesses, movements. They could be studied and catalogued, but the space in between seemed to contain nothing worth investigating. It was just the darkness that separated the interesting things. This started to change in the early 1800s. Astronomers were getting better at measuring the brightness and colours of stars. They were building more powerful telescopes, developing better techniques for recording what they saw. And as they studied stars at different distances, some of them started to notice something strange. Stars that were very far away seemed slightly fainter and slightly redder than they should have been based on their type. Not by a lot. The effect was subtle, but it was consistent. The farther away a star was, the more its light seemed to be dimmed and reddened compared to what you'd expect. At first, many astronomers dismissed this. They assumed it was measurement error, or that distant stars were simply intrinsically different from nearby ones. But a few researchers took the observation seriously and started asking a different question. What if there's something between us and those distant stars? What if there's some material in the line of sight, too thin to see directly, but present in enough quantity across vast distances to slightly absorb and scatter starlight passing through it? This idea was controversial at first. The vacuum of space was deeply ingrained in astronomical thinking. Most astronomers at the time considered it almost self-evident that the space between stars was perfectly empty. But the evidence kept building, and it kept pointing in the same direction. In 1847, a German astronomer named Friedrich Georg Wilhelm Struve published work suggesting that starlight was being absorbed by material in interstellar space. He studied how the apparent brightness of stars decreased with distance and argued that the dimming was greater than you'd expect from distance alone. Something was absorbing some of the light on its way to Earth. His work didn't gain immediate acceptance, partly because the effect was so small and difficult to measure precisely with the technology available at the time. But the seed was planted. The real breakthrough came in the early 20th century. In 1930, a Swiss-American astronomer named Robert Trumpler was studying star clusters, groups of stars that form together and remain relatively close to each other. Trumpler measured the distances to these clusters using two different methods. One method was based on the apparent size of the clusters, how big they looked in the sky. The other was based on the apparent brightness of the stars within them. If both methods were measuring the same distance, they should have given the same answer. But they didn't. The brightness-based distances were consistently larger than the size-based distances. The stars appeared fainter than they should have been at their true distances. Trumpler realized the explanation was that something in the space between us and the clusters was absorbing starlight, making the stars appear dimmer and therefore appear to be farther away than they really were. He called this effect interstellar extinction. Light was being lost, extinguished, as it passed through the vast reaches of space between stars. And the agent responsible for this extinction turned out to be tiny solid particles. Dust. Not the kind of dust you find under your bed. Not pollen or skin cells or dirt. Interstellar dust is made of microscopic grains far smaller than anything you can see with your eyes. These grains are typically just fractions of a micrometer in size. A micrometer is a millionth of a meter. These dust particles are hundreds of times smaller than the width of a human hair. They're made of silicates, which are minerals similar to sand and rock on Earth, and carbon compounds, including forms of carbon similar to soot. Some grains are coated with thin layers of frozen water, carbon dioxide, methane, and ammonia. These tiny particles are scattered incredibly thinly throughout interstellar space. But just like the gas atoms, their effects accumulate over the enormous distances between stars. When starlight passes through a region of interstellar dust, the dust grains scatter and absorb some of the light. Shorter wavelengths of light, which we perceive as blue, are scattered more effectively than longer wavelengths, which we perceive as red. This is actually the same basic physics that makes the sky blue on Earth. Air molecules scatter blue sunlight more than red sunlight, which is why the sky appears blue when you look away from the sun. In interstellar space, dust grains do something similar. They scatter the blue light from distant stars more than the red light. The result is that distant stars appear redder than they actually are. Astronomers call this interstellar reddening. It was this reddening combined with the overall dimming that gave away the presence of interstellar dust. The dust was too thin to see directly. No telescope could look out into the space between stars and see individual dust grains floating around. But the collective effect of trillions upon trillions of these microscopic particles spread across light years of space was measurable. It changed the color and brightness of starlight in a way that could be detected and quantified from Earth. This was a major discovery. It meant that the space between stars was not a perfect vacuum after all. There was material out there, real physical stuff, spread so thinly that you could never detect it locally, but present in vast enough quantities across interstellar distances to have measurable effects on the light passing through it. And if there was dust, there was almost certainly gas too, since dust grains form from gas and are always found alongside it in astrophysical environments. The evidence for interstellar gas came through a different channel. In 1904, a German astronomer named Johannes Hartmann was studying the spectrum of a binary star system called Delta Orionis, one of the stars in Orion's belt. When astronomers spread starlight into a spectrum, they can see dark lines at specific wavelengths where atoms in the star's atmosphere have absorbed light. As the two stars in a binary system orbit each other, these absorption lines shift back and forth because of the Doppler effect. The stars are moving toward us and then away from us as they orbit, which shifts the wavelengths of their light. Hartmann expected all the absorption lines to shift together, but he noticed something peculiar. One particular absorption line, caused by calcium atoms, didn't shift at all, while all the other lines moved back and forth with the star's orbital motion. This one calcium line stayed perfectly still. Hartmann realized that this stationary line wasn't coming from the stars themselves. It was coming from calcium atoms floating in the space between the stars and Earth. These atoms were not orbiting with the binary stars. They were sitting in interstellar space, absorbing light at a specific wavelength as the starlight passed through them on its way to Earth. This was the first direct detection of interstellar gas. There were atoms out there between the stars, not many. The absorption line was faint, indicating a very small amount of calcium. But it was there. And where there was calcium, there was almost certainly hydrogen and other elements too. Since calcium is relatively rare compared to hydrogen in the universe, over the following decades, astronomers found more and more evidence for interstellar gas. They detected absorption lines from sodium, potassium, iron, and other elements in the spectra of distant stars. Each detection confirmed that atoms were floating in the space between the stars, too thinly spread to see directly, but detectable through their effect on starlight. By the mid-20th century, the picture was becoming clear. The space between the stars contained both gas and dust, spread incredibly thinly, but filling the vast volumes of interstellar space. The gas was primarily hydrogen, the simplest and most abundant element in the universe. About 90% of the atoms in interstellar space are hydrogen. About 9% are helium, the second lightest element. The remaining 1% or so includes all the heavier elements: carbon, nitrogen, oxygen, iron, silicon, and dozens of others, in trace amounts. The dust made up only about 1% of the total mass of interstellar material, with gas accounting for the other 99%. but that 1% of dust had an outsized impact because of how effectively it absorbed and scattered light. In some directions, when you look through particularly dense accumulations of interstellar dust, entire regions of the sky appeared dark, not because there were no stars behind them, but because the dust was so thick that it blocked the light from reaching us. These dark patches had actually been observed for centuries. The astronomer William Herschel, looking at a particularly dark region in the constellation Scorpius in the late 1700s, famously declared that it was a hole in the sky. He thought he was seeing an actual gap in the distribution of stars, a place where stars simply didn't exist. But he was wrong. There were stars behind that dark patch. They were simply hidden behind a dense cloud of interstellar dust that absorbed their light before it could reach Earth. Today, we know these dark regions as dark nebulae, clouds of gas and dust so dense that they block the light from stars behind them. Some of them are enormous. The Coalsack Nebula, visible in the southern sky near the Southern Cross, is about 600 light-years away and spans roughly 60 light-years across. It appears as a dark patch against the bright background of the Milky Way. The dust within it is dense enough, at least by interstellar standards, to block virtually all the visible light from the stars behind it. But dense is a relative term here. Even in the darkest, thickest dark nebulae, the density of material is incredibly low by earthly standards. A dense molecular cloud might have a few hundred to a few thousand molecules per cubic centimeter. That sounds like a lot more than the average interstellar density of 1 atom per cubic centimeter. And it's hundreds or thousands of times denser than the average. But compared to the air in this room, with its 25 billion molecules per cubic centimeter, even the densest interstellar cloud is a staggeringly good vacuum. You could fly through the densest molecular cloud in the galaxy and you would not feel it. You would not see it with your eyes unless you looked at how it affected the light from stars behind it. It would seem like perfect emptiness. And yet, these clouds contain enough material to form stars. They contain enough gas and dust that gravity can pull it together over millions of years, compressing it, heating it, until nuclear fusion ignites and a new star is born. The entire life cycle of stars, from birth to death, is intimately connected to the material that fills interstellar space. Stars are born from it. They spend their lives surrounded by it. And when they die, they return material to it, enriching it with heavier elements that will be incorporated into the next generation of stars and planets. This is the fundamental insight that transforms how we think about the space between the stars. It's not just a gap. It's not just emptiness separating the important things. The interstellar medium, the gas and dust that fills the space between the stars, it is itself a crucial part of the story. It's the raw material of the galaxy. It's the reservoir from which stars draw their substance and to which they return it when they die. Without it, no new stars would form. Without it, the galaxy would be a static collection of aging stars, slowly burning out with no possibility of renewal. The darkness between the stars is not the absence of something. It's the presence of something so thinly spread that it's invisible to our eyes but essential to everything we see. Every star in the night sky, every planet, every moon, every grain of sand on every beach on Earth, all of it was once part of the interstellar medium. All of it was once atoms and dust grains floating in the darkness between ancient stars that have long since died. The material that makes up your body passed through interstellar space. It drifted in the cold darkness for millions of years before gravity pulled it together into the cloud that became our solar system. You are made of interstellar material. And when the sun eventually dies, billions of years from now, some of that material will be returned to interstellar space, to drift once again in the darkness, waiting to become part of something new. So what began as an apparent void, a gap between the interesting objects, turned out to be something far more profound. The space between the stars is an environment. It has physical properties. It has density, temperature, composition, and structure. It changes over time. It interacts with the stars embedded within it. It is shaped by their energy, and in turn shapes the next generation of stars that will form from it. Astronomers gave this environment a name. They called it the interstellar medium. And understanding the interstellar medium turned out to be essential to understanding how galaxies work, how stars are born, how the elements that make up planets and life are distributed across space, and how the universe evolves over time. What seemed like nothing turned out to be one of the most important things in all of astrophysics. And we've only just scratched the surface, because the interstellar medium isn't just gas and dust floating passively in the dark. It's threaded with magnetic fields. It's bathed in radiation. It's peppered with particles moving at nearly the speed of light. It has temperature, it has pressure, it has phases, like water can be ice or liquid or steam. The interstellar medium can be cold or hot, neutral or ionized, dense or thin, calm or turbulent. It's a dynamic, active, structured environment hidden in what looks like empty darkness. And understanding all of these layers, all of these hidden properties, is what we're going to explore next. So now we know the space between stars isn't empty. There's material out there. Incredibly thin, impossibly sparse, but real. Astronomers call this material the interstellar medium. And that name, the interstellar medium, is the formal term for everything that exists in the space between star systems within a galaxy. Not between galaxies. That's a different environment called the intergalactic medium. The interstellar medium is specifically the material that fills the space between the stars inside a galaxy like the Milky Way. And it turns out this material is far more complex, far more varied, and far more important than anyone imagined when it was first discovered. Let's break it down. The interstellar medium is made up of two main components: gas and dust. About 99% of it by mass is gas. The remaining 1% is dust, those tiny solid particles we talked about earlier. Now, 1% might sound negligible, and in terms of mass, it is a small fraction. But that 1% of dust has an enormous impact on what we can see and how the galaxy behaves. We'll come back to the dust shortly. First, let's focus on the gas because it's the dominant component by far, and it holds the key to understanding how the interstellar medium works. As we've established, the gas is overwhelmingly hydrogen and helium, the original elements forged in the Big Bang about 13.8 billion years ago. They are the primordial raw material the universe started with. But that remaining roughly 1% of heavier elements, the carbon, oxygen, iron, silicon, magnesium, sulfur, and dozens more, that tells a different story. Almost every one of those atoms was forged later inside stars through nuclear fusion, or created in the catastrophic explosions when massive stars die. That 1% is what makes rocky planets possible. It's what makes life possible. Without it, the universe would contain nothing but hydrogen and helium gas. And there would be no planets, no water, no organic chemistry, and no life. Now, hydrogen in interstellar space doesn't all behave the same way. It exists in 3 fundamentally different forms depending on the conditions around it. And understanding these 3 forms is essential to understanding the interstellar medium because they occupy different regions of space, have different temperatures, different densities, and play different roles in the life cycle of the galaxy. The first form is atomic hydrogen. This is individual hydrogen atoms floating freely through space. Each atom consists of 1 proton and 1 electron. In this state, the hydrogen is electrically neutral. It's not ionized, meaning it hasn't lost its electron, and it's not bound to another hydrogen atom. It's just a single neutral atom drifting through the void. Atomic hydrogen is the most common form of hydrogen in the galaxy by volume. It fills enormous regions of interstellar space at temperatures of a few thousand degrees up to about 10,000 degrees. At these temperatures, the atoms have enough energy to move around freely, but not enough to lose their electrons. Atomic hydrogen was first detected in interstellar space through radio astronomy. In 1944, a Dutch astronomer named Hendrik van der Hulst predicted that neutral hydrogen atoms should emit radio waves at a very specific wavelength, 21 centimeters. This prediction was based on quantum mechanics. Inside a hydrogen atom, the electron and proton each have a property called spin. When the spins are aligned in the same direction, the atom has slightly more energy than when they're aligned in opposite directions. When the spin of the electron spontaneously flips from the higher energy state to the lower one, the atom releases a tiny amount of energy as a radio photon with a wavelength of exactly 21 centimeters. For any individual atom, this spin flip is incredibly rare. On average, it happens only once every about 10 million years for a given atom. But there are so many hydrogen atoms in interstellar space, trillions upon trillions upon trillions of them spread across the galaxy, that at any given moment, enormous numbers of them are undergoing this transition. The collective signal is strong enough to detect with radio telescopes on Earth. In 1951, 3 separate groups of astronomers detected this 21 centimeter emission from interstellar hydrogen almost simultaneously. One group was in the Netherlands, led by Hendrik van der Hulst himself, along with Jan Oort and C. Alex Muller. One was in the United States, led by Harold Ewan and Edward Purcell at Harvard University. And one was in Australia at the Commonwealth Scientific and Industrial Research Organisation. This discovery revolutionized our understanding of the galaxy. For the first time, astronomers could map the distribution of hydrogen gas throughout the Milky Way. Optical telescopes could only see stars and the effects of dust. They were blind to the gas itself. But radio waves at 21 centimeters pass right through interstellar dust without being absorbed or scattered. So radio telescopes could peer into regions of the galaxy that were completely hidden at visible wavelengths, including the galactic center and the far side of the galaxy beyond it. Using 21 centimeter observations, astronomers mapped the spiral structure of the Milky Way for the first time. They could see where the gas was concentrated and where it was thin. They discovered that hydrogen gas is not spread uniformly throughout the galaxy. It's concentrated in the spiral arms and thin in the regions between them. This was one of the first pieces of evidence that the Milky Way is a spiral galaxy. The second form of hydrogen in interstellar space is ionized hydrogen. This is hydrogen that has been stripped of its electron, When a hydrogen atom loses its electron, it becomes a bare protons carrying a positive electric charge. This happens when hydrogen is exposed to intense ultraviolet radiation, typically from hot young stars. The ultraviolet photons carry enough energy to knock electrons off hydrogen atoms, ionizing the gas. Regions of ionized hydrogen are some of the most visually spectacular objects in the galaxy. They're called H2 regions, using the Roman numeral 2 to indicate that the hydrogen is in its second ionization state, which for hydrogen simply means it's fully ionized. When astronomers say H2 region, they mean a cloud of gas where the hydrogen has been ionized by nearby hot stars. These regions glow because when free electrons in the gas are recaptured by protons, the atoms emit light as the electrons cascade down through energy levels. The characteristic pinkish-red glow of many nebulae comes from this process. The Orion Nebula, one of the most famous objects in the night sky, visible to the naked eye as a fuzzy patch in the sword of Orion, is an H2 region. It's about 1,344 light-years away and roughly 24 light-years across. At its heart are 4 hot young stars called the trapezium, whose intense ultraviolet radiation ionizes the surrounding gas, making it glow. The Orion Nebula is a relatively small H2 region. Some are vastly larger. The Tarantula Nebula in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, is about 930 light-years across. It contains some of the most massive and luminous stars known. If the Tarantula Nebula were at the distance of the Orion Nebula, it would cover a substantial portion of the night sky and cast visible shadows on the ground. These H2 regions are important because they mark sites of recent star formation. Hot young stars are born inside dense clouds of gas. Their ultraviolet radiation then ionizes the surrounding gas, creating a glowing bubble. The glow is essentially a signpost saying new stars were born here recently. By mapping H2 regions across the galaxy, astronomers can identify where star formation is actively happening right now. The third form of hydrogen is molecular hydrogen. This is 2 hydrogen atoms bonded together to form a molecule, written as H2 using the subscript 2. Molecular hydrogen is the form that hydrogen takes in the coldest, densest regions of interstellar space. In these environments, temperatures drop to just a few degrees above absolute zero, around 10 to 20 Kelvin, which is roughly minus 250 to minus 260 degrees Celsius. At these frigid temperatures, hydrogen atoms move slowly enough that when they encounter each other on the surface of a dust grain, they can stick together and form molecules. This is a crucial detail. Molecular hydrogen doesn't form easily in open space. 2 hydrogen atoms colliding in a vacuum will usually just bounce off each other. They need a surface, a tiny dust grain, to act as a catalyst. The atoms land on the grain's surface, find each other, bond, and then the newly formed molecule is released back into space. Without dust, there would be far less molecular hydrogen. And without molecular hydrogen, the process of star formation would be fundamentally different, perhaps impossible in the way we observe it. Molecular hydrogen is found in enormous structures called molecular clouds. These are the densest parts of the interstellar medium, containing hundreds to thousands of molecules per cubic centimeter. That's still incredibly thin by earthly standards. Remember, the air you're breathing has about 25 billion molecules per cubic centimeter. But it's hundreds or thousands of times denser than the average interstellar medium. Molecular clouds are big, really big. A typical giant molecular cloud might be 100 to 300 light years across and contain enough mass to make hundreds of thousands or even millions of stars. The total mass of a single giant molecular cloud can exceed 1,000,000 times the mass of our Sun. Some of the most famous molecular clouds are in the constellation Orion. The Orion Molecular Cloud Complex is a vast structure about 1,300 light years away that spans hundreds of light years. It contains several active star-forming regions, including the Orion Nebula. Inside this complex, new stars are being born right now, condensing out of the cold, dense gas under the pull of gravity. Molecular clouds are cold and dark. Because they're filled with dust as well as gas, they block light from stars behind them. When you look at the Milky Way on a dark night, you can see dark lanes and patches interrupting the bright band of starlight. Many of these dark features are molecular clouds silhouetted against the brighter background. They look like holes in the stars, but they're actually dense clouds of gas and dust sitting in front of the more distant starlight. The Horsehead Nebula in the constellation Orion is a famous example. It's a dark cloud of molecular gas and dust shaped roughly like a horse's head, silhouetted against a bright background of glowing ionized hydrogen. It's a stunning visual reminder that darkness in the sky doesn't mean emptiness. It means something is there, blocking the light. Inside a molecular cloud, conditions are extreme by interstellar standards. The temperature is just a few degrees above absolute zero. The density, while still a near-perfect vacuum by earthly standards, is high enough that gravity can begin to overcome the internal pressure of the gas. When a region within a molecular cloud becomes dense enough, it starts to collapse under its own gravity. The gas falls inward, compressing, heating up. As the collapse continues, the center becomes hotter and denser. Eventually, when the temperature and pressure at the core reach about 10 million degrees, nuclear fusion ignites. Hydrogen atoms begin fusing into helium, releasing enormous amounts of energy. A new star is born. This is how every star in the night sky was formed. Every single one, including our Sun. About 4.6 billion years ago, a region within a molecular cloud somewhere in the Milky Way became unstable and began to collapse. Perhaps a shockwave from a nearby supernova explosion compressed the gas just enough. Perhaps the gravitational influence of a passing star disturbed the cloud. Whatever the trigger, the center of that collapsing region became the Sun. The surrounding material flattened into a disk, and within that disk, dust grains stuck together grew into pebbles, then rocks, then planetesimals, and eventually into the planets of our solar system. Earth formed from the gas and dust of the interstellar medium. The water in your body, the calcium in your bones, the iron in your blood, all of it was once part of a cold, dark molecular cloud floating in the space between ancient stars. Now let's turn to the dust in more detail because interstellar dust deserves its own attention. It makes up only about 1% of the interstellar medium's mass, but its effects are far out of proportion to its quantity. Interstellar dust grains are tiny. Most are between about 1/10 of a micrometer and 1 micrometer in size, far smaller than a human hair as we mentioned. But here's what might surprise you. Some grains are so small, they approach the wavelength of visible light itself. That means they interact with light not by simply blocking it like a wall, but by scattering and diffracting it. which is why their effect on starlight is wavelength dependent. You could never see one with your naked eye. You'd need an electron microscope to study an individual grain. What are these grains made of? The composition varies, but there are two main types. Silicate grains are made of silicon and oxygen combined with metals like magnesium and iron, forming minerals similar to olivine and pyroxene, the same types of minerals found in rocks on Earth. Carbonaceous grains are made primarily of carbon in various forms, including graphite-like structures and complex organic molecules called polycyclic aromatic hydrocarbons. Some grains have cores of silicate or carbon surrounded by mantles of frozen volatile compounds, ices made of water, carbon dioxide, methane, and ammonia. These icy mantles form in the coldest, densest regions of the interstellar medium, where temperatures are low enough for these substances to freeze onto the surfaces of existing grains. Where does interstellar dust come from? It's created by stars. When stars reach the end of their lives, they shed material back into space. Low and intermediate mass stars like our Sun will eventually swell into red giants and blow off their outer layers as planetary nebulae. The expanding gas cools as it moves away from the star. And as it cools, atoms begin to condense into tiny solid particles. Dust grains form in these outflowing winds, like snowflakes forming in cooling air. Red giant stars are among the most prolific dust producers in the galaxy. A single red giant can lose a significant fraction of its mass through stellar winds over the course of its later life, and much of that lost material condenses into dust. Massive stars that explode as supernovae also produce dust. The expanding debris from a supernova explosion contains heavy elements forged in the star's core and during the explosion itself. As this debris expands and cools, some of those heavy elements condense into dust grains. Some dust also forms in the dense winds of very massive stars called Wolf-Rayet stars, which blow off enormous amounts of material before they explode. So the dust between the stars was literally manufactured inside stars that lived and died before our Sun was born. Interstellar dust does several important things. First, it absorbs and scatters starlight. This is the interstellar extinction and reddening that we discussed earlier. Dust makes distant stars appear fainter and redder than they really are. At visible wavelengths, dust can completely block our view of objects behind it. The center of the Milky Way, for example, is completely invisible at optical wavelengths, because there's so much dust between us and the galactic center that it absorbs virtually all the visible light. We can only see the galactic center at infrared and radio wavelengths, which pass through dust much more easily than visible light. Second, dust grains absorb starlight and re-emit the energy as infrared radiation. When a dust grain absorbs a visible or ultraviolet photon from a nearby star, the grain heats up slightly and then radiates that energy back into space at much longer wavelengths, in the infrared part of the spectrum. This means that interstellar dust glows in the infrared. In fact, a significant fraction of the total light output of our galaxy is in the infrared, produced not by stars directly but by dust grains that have absorbed starlight and re-emitted it at longer wavelengths. Infrared telescopes like the Spitzer Space Telescope and the Herschel Space Observatory have mapped this dust emission across the galaxy, revealing the distribution of dust in extraordinary detail. Third, and perhaps most importantly for the existence of life, dust grains serve as surfaces where chemical reactions can happen. In the cold, sparse conditions of interstellar space, atoms and molecules rarely encounter each other. The densities are so low that collisions between atoms are infrequent. But when atoms land on the surface of a dust grain, they can stick there, find other atoms, and react. Molecular hydrogen, as I mentioned, forms almost exclusively on the surfaces of dust grains. But hydrogen isn't the only molecule formed this way. Water molecules can form on grain surfaces when oxygen atoms react with hydrogen. More complex molecules, including simple organic compounds, can form through surface reactions on grains in cold, dense clouds. Well over 200 different molecules have been detected in the interstellar medium so far. Some of them are surprisingly complex. Astronomers have found ethyl alcohol, the same type of alcohol found in beer and wine, floating in interstellar clouds. They've found amino acid precursors, glycolaldehyde, which is a simple sugar, and even fullerenes, soccer ball-shaped molecules made of 60 carbon atoms. They've detected formaldehyde, hydrogen cyanide, acetic acid, and acetaldehyde. In 2014, astronomers using the Atacama Large Millimeter Array in Chile detected isopropyl cyanide in a molecular cloud near the center of the Milky Way. This molecule has a branched carbon chain structure, the same kind of branching found in amino acids, the building blocks of proteins. Its discovery suggested that the chemical complexity available in interstellar space might be even greater than previously thought. These molecules form through a combination of gas phase reactions and grain surface chemistry. The interstellar medium is not just a reservoir of simple atoms. It's a vast, cold, incredibly slow chemistry lab where the building blocks of life are assembled over millions of years. When a molecular cloud collapses to form a new star and planetary system, all of these molecules come along for the ride. They're incorporated into the protoplanetary disk, into the comets and asteroids that form within it, and eventually onto the surfaces of newborn planets. Earth may have received a significant portion of its water and organic molecules from comets and asteroids that formed from interstellar material enriched with these compounds. Now, let's talk about the large-scale distribution of all this material, because the interstellar medium is not spread evenly throughout the galaxy. It has structure at every scale. At the largest scale, gas and dust are concentrated in the disk of the Milky Way. The Milky Way is a flat spiral galaxy. Its disk is roughly 100,000 light-years across, but only about 1,000 to 2,000 light-years thick. Most of the interstellar gas and dust is confined to this thin disk, concentrated especially in the spiral arms. When you look at a spiral galaxy from the outside, like the beautiful images of galaxies taken by the Hubble Space Telescope, the spiral arms appear bright because they contain lots of young hot stars. But they also contain most of the galaxy's gas and dust. The spiral arms are essentially waves of compression that move through the galactic disk. As gas enters a spiral arm, it gets compressed. This compression increases the density of the gas, which can trigger the collapse of molecular clouds and the formation of new stars. So the spiral arms are where most star formation happens in a spiral galaxy. And star formation is intimately tied to the interstellar medium, because stars form from the interstellar medium and return material to it when they die. Within the spiral arms, the interstellar medium is organized into structures at many different scales. Giant molecular clouds, the largest coherent structures in the interstellar medium, are typically found in the spiral arms. They can be hundreds of light years across and contain millions of solar masses of gas. Within a giant molecular cloud, you find denser substructures, clumps of gas tens of light years across with densities of thousands of molecules per cubic centimeter. Within those clumps, you find even denser cores, compact regions less than a light year across, where densities reach tens of thousands or even hundreds of thousands of molecules per cubic centimeter. These cores are the specific sites where individual stars or small groups of stars form. So, the interstellar medium has a nested hierarchical structure. At the larger scale, gas fills the galactic disk. Within the disk, it concentrates in spiral arms. Within the spiral arms, it forms giant molecular clouds. Within those clouds, it forms clumps. Within the clumps, it forms cores. And within the cores, stars are born. Each level of this hierarchy spans a different range of sizes and densities, from the 100,000 light-year galactic disk down to the fraction of a light-year dense core that will become a single star. Outside the molecular clouds, in the more diffuse regions of the interstellar medium, the gas exists primarily as atomic hydrogen. This warmer, more tenuous gas fills much of the volume of the galactic disk. It's less dense than the molecular clouds, typically just a few atoms per cubic centimeter, and much warmer, with temperatures of several thousand degrees. This warm atomic gas is the background medium in which the denser molecular clouds are embedded. It's like an ocean, and the molecular clouds are islands within it. Denser, colder, and chemically richer than their surroundings. The warm atomic medium doesn't form stars on its own. It's too thin and too warm for gravity to overcome its internal pressure. But it serves as the reservoir from which denser clouds can form over time when compressed by a spiral arm passage or a distant supernova shockwave. There are also regions where the gas is even thinner and hotter than the warm atomic medium. Near hot stars, near supernova remnants, and in other energetic environments, the gas can be heated to temperatures of hundreds of thousands or even millions of degrees. At these extreme temperatures, the gas is fully ionized. Every atom has been stripped of its electrons. This creates a plasma, a state of matter where electrons and ions move freely. Hot ionized gas fills large volumes of the galaxy, particularly in the regions above and below the galactic disk, forming what's called the galactic halo. We'll explore these extreme environments and the forces that create them in more detail as we continue. But for now, the essential point is this. The interstellar medium is not a uniform void. It's a complex structured environment with regions that vary enormously in density, temperature, and chemical composition. Some regions are cold and dense, packed with molecules and dust, dark and opaque, the nurseries of new stars. Other regions are warm and diffuse, filled with atomic hydrogen, transparent and quiet. Still other regions are blisteringly hot, blasted by radiation and supernova explosions. Thin almost beyond measurement, but searingly energetic. All of these regions coexist within the galaxy, connected and interacting, exchanging material and energy in a slow dynamic cycle that has been running for billions of years. And all of it, every atom of hydrogen, every grain of dust, every molecule drifting in the cold darkness, is part of the hidden substance that fills what looks like empty space between the stars. You can't see it when you look up at the night sky, but it's there. It has always been there, and without it, nothing you see in the sky, not a single star, not a single planet, not even the atoms in your own body, would exist. So far, We've explored the gas and dust that fill interstellar space. We've learned that the space between the stars contains a thin but real material made of hydrogen, helium, heavier elements, and microscopic solid grains. We've seen how this material is organized into structures ranging from diffuse atomic gas to cold, dense molecular clouds where new stars are born. But gas and dust are only part of what exists between the stars, because the interstellar medium is also threaded with invisible forces and filled with energy that you cannot see, cannot touch, and in most cases cannot directly detect without specialized instruments. And these invisible components, magnetic fields, cosmic rays, and radiation are just as important to the story of interstellar space as the matter itself. In some ways, they're even more important because they shape how that matter behaves, how it moves, how it collapses, and ultimately whether or not new stars and planets can form. Let's start with magnetic fields, because the galaxy is magnetic. Not in the way a refrigerator magnet is magnetic, not in any way you would notice in everyday life, but the entire Milky Way is permeated by a magnetic field that stretches across tens of thousands of light years, threading through the gas and dust of the interstellar medium like an invisible web. This galactic magnetic field is incredibly weak by terrestrial standards. On Earth, the magnetic field at the surface is roughly half a Gauss. A Gauss is a unit of magnetic field strength. A refrigerator magnet might produce a field of about 50 Gauss. A medical MRI machine produces a field of about 10,000 to 30,000 Gauss. The magnetic field in the interstellar medium is roughly 1 to 10 microgauss. A microgauss is a millionth of a Gauss. So the interstellar magnetic field is about 100,000 to 1,000,000 times weaker than the Earth's magnetic field. It's fantastically, almost immeasurably weak, and yet, across the vast distances of interstellar space, this incredibly faint magnetic field has enormous consequences. The reason is the same principle we've encountered before with interstellar gas. The field is weak at any single point, but it extends across light years, across tens of light years, across hundreds of light years. And when you integrate even a tiny force over such enormous distances, the cumulative effect becomes significant. The interstellar magnetic field influences the motion of charged particles in interstellar space. Any particle that carries an electric charge, and that includes ionized atoms, free electrons, and cosmic ray particles, doesn't travel in a straight line through a magnetic field. Instead, it spirals around the magnetic field lines, corkscrewing along them. The particle is effectively trapped, forced to follow the field. This means that the magnetic field acts as an invisible guide, channeling the movement of charged matter throughout the galaxy. It doesn't stop the matter from moving, but it constrains the directions in which it can move. Charged particles can slide freely along field lines, but have difficulty crossing them. This has profound implications for the structure of the interstellar medium. In molecular clouds, where stars are born, the magnetic field can resist gravitational collapse. When a cloud of gas starts to contract under its own gravity, the magnetic field lines running through it get compressed along with the gas. But magnetic fields resist compression. They push back. This magnetic pressure can slow down or even prevent the collapse of a cloud, supporting it against gravity like an invisible scaffolding. For a molecular cloud core to collapse and form a star, it has to overcome not just its own internal thermal pressure, but also the magnetic pressure of the field lines running through it. This means that the magnetic field effectively regulates star formation. Without it, molecular clouds would collapse much more quickly, and stars would form much faster than they actually do. The magnetic field acts as a brake, slowing the process down and controlling the rate at which new stars are born in the galaxy. Astronomers have estimated that without magnetic support, the Milky Way would convert all of its interstellar gas into stars in just a few 100 million years. Instead, the process has been going on for billions of years, and the galaxy still has substantial reserves of gas. The magnetic field is one of the main reasons why. How do we know the interstellar magnetic field exists if it's so incredibly weak? We can't see it directly. We detect it through its effects. One of the primary methods involves the polarization of starlight. When starlight passes through a region of interstellar dust, the dust grains don't scatter the light equally in all directions. Interstellar dust grains are not spherical. They're elongated, like tiny rods or flattened disks. And in a magnetic field, these elongated grains tend to align themselves with their long axes perpendicular to the field lines. It's similar to how iron filings line up in the presence of a magnet on a tabletop. When starlight passes through a cloud of aligned dust grains, the light becomes polarized. One orientation of light wave passes through more easily than another. By measuring the polarization of light from many distant stars, astronomers can map the direction of the magnetic field across the sky. This technique has been used for decades and has revealed the large-scale structure of the galactic magnetic field. It runs roughly along the spiral arms of the Milky Way, following the general flow of gas in the galactic disk, but with complex local variations, twists, tangles, and reversals that reflect the turbulent history of the interstellar medium. Another method uses radio waves. Charged particles spiraling around magnetic field lines emit a type of radiation called synchrotron radiation. This radiation is most prominent at radio wavelengths and is polarized, meaning its electric field oscillates in a specific direction related to the orientation of the magnetic field. By observing synchrotron emission from the Milky Way and from other galaxies, astronomers can map magnetic fields on galactic scales. Radio observations have revealed that the Milky Way's magnetic field has a complex structure with a large-scale component that follows the spiral arms and a turbulent component that varies on smaller scales, driven by supernova explosions, stellar winds, and other energetic events. The magnetic field of the galaxy is not static. It's dynamic, constantly being amplified, stretched, twisted, and reorganized by the motions of the ionized gas in which it's embedded. Now let's talk about cosmic rays, because these are among the most remarkable things that fill interstellar space. Cosmic rays are not rays at all, despite the name. They're particles. Individual atoms or atomic nuclei stripped of their electrons, traveling through space at incredible speeds. Most cosmic rays are protons, the nuclei of hydrogen atoms. About 10% are helium nuclei, also called alpha particles. The remaining few percent are nuclei of heavier elements, and there's also a small component of electrons. What makes cosmic rays extraordinary is their energy. These particles are moving at speeds very close to the speed of light. Some cosmic rays have energies that are almost beyond belief. The most energetic cosmic ray ever detected, observed in 1991 by the Fly's Eye experiment in Utah, had an energy of about 3 × 10 to the 20th electron volts. That's a single subatomic particle carrying the kinetic energy of a baseball thrown at about 100 kilometers per hour. All that energy concentrated in a single proton, The particle was moving so close to the speed of light that if it raced a photon across the entire 100,000 light-year width of the Milky Way, the photon would finish only about 4 millimeters ahead. Physicists nicknamed it the "oh my god" particle because of the sheer disbelief its energy provoked. Where do cosmic rays come from? Most of the cosmic rays we detect in our region of the galaxy are believed to be accelerated by supernova remnants. When a massive star explodes as a supernova, the blast wave expands outward into the interstellar medium at speeds of thousands of kilometers per second. Charged particles caught in this expanding shock wave can bounce back and forth across the shock front, gaining energy with each crossing. This process, called diffusive shock acceleration or Fermi acceleration, can boost particles to tremendous energies over thousands of years as the supernova remnant expands. Each time a charged particle crosses the shock front, it picks up a little more energy. After thousands or millions of crossings, the particle has been accelerated to a significant fraction of the speed of light. The supernova remnant acts like a giant particle accelerator, using its expanding shockwave to pump energy into individual protons and nuclei until they're moving at nearly light speed. This process has been confirmed by observations. Gamma-ray telescopes have detected high-energy radiation coming from a supernova remnants, consistent with the interaction of cosmic ray particles with the surrounding gas. X-ray telescopes have imaged the thin shock fronts of supernova remnants where the acceleration is happening. The connection between supernovae and cosmic rays is well established, at least for the majority of cosmic rays with moderate energies. The most energetic cosmic rays, the ultra-high energy particles like the oh my god particle, probably come from even more extreme sources. Active galactic nuclei, the supermassive black holes at the centers of other galaxies that are actively consuming matter and producing enormous jets of energy, are leading candidates. Gamma-ray bursts, the most energetic explosions in the universe, are another possibility. These sources can accelerate particles to energies far beyond what a supernova remnant can achieve. Cosmic rays fill the entire volume of the galaxy. They're everywhere in interstellar space, streaming through the darkness at nearly the speed of light in every direction. They don't follow straight paths because the galactic magnetic field bends their trajectories, causing them to spiral and wander through interstellar space for millions of years before eventually escaping the galaxy or losing their energy through collisions. At any given moment, cosmic ray particles are passing through you. Right now, as you listen to this, about one cosmic ray particle is passing through every square centimeter of your body every second. Most of these are relatively low energy and harmless. Your body is constantly bombarded by cosmic rays and always has been. They're part of the natural background radiation of life on Earth. But cosmic rays are not just interesting as high-energy curiosities. They play an important role in the physics of the interstellar medium. Cosmic rays are one of the main sources of ionization in the cold, dense interiors of molecular clouds. Remember, molecular clouds are cold and dark. They're shielded from ultraviolet radiation by the dust surrounding them. Without ultraviolet radiation to ionize the gas, you might expect that the gas inside a molecular cloud would be completely neutral, with no free electrons or ions at all, but cosmic rays can penetrate where ultraviolet light cannot. A high-energy proton traveling at nearly the speed of light can pass through the dust and gas of a molecular cloud almost unimpeded. When it does interact with a molecule in the cloud, it can knock an electron loose, ionizing the molecule. This low level of ionization maintained by cosmic rays inside molecular clouds is crucial because it allows the magnetic field to couple to the gas. If the gas were completely neutral, the magnetic field wouldn't be able to exert any force on it. Magnetic fields only directly affect charged particles. But because cosmic rays maintain a small fraction of ionized particles throughout the cloud, the magnetic field can grip the gas through these ions, influencing the cloud's behavior and its ability to collapse and form stars. Cosmic rays also deposit energy in the gas they pass through. When a cosmic ray ionizes a molecule, the freed electron carries kinetic energy that gets converted into heat as the electron collides with surrounding molecules. This cosmic ray heating is one of the dominant heating mechanisms in the deep interiors of molecular clouds, where other sources of heat, like starlight, can't penetrate. The temperature of a molecular cloud core, which determines its internal pressure and therefore its ability to resist gravitational collapse, is set in part by the balance between cosmic ray heating and radiative cooling. So cosmic rays influence not just the ionization, but the temperature structure of the regions where stars form. Now let's turn to radiation, because interstellar space is not dark. It seems dark to human eyes because we can only see a narrow slice of the electromagnetic spectrum, the part we call visible light. But if you could see all wavelengths of electromagnetic radiation, interstellar space would be glowing. It would be filled with light of every wavelength, from the longest radio waves to the shortest gamma rays. Each type of radiation tells a different story about the interstellar medium and the processes happening within it. Start with starlight. The combined light of all the stars in the galaxy fills interstellar space with a diffuse background glow. This interstellar radiation field is dominated by visible and near-infrared light from ordinary stars like the Sun, but it also includes significant contributions of ultraviolet light from hot massive stars. Even though hot stars are rare compared to cooler stars, they produce enormous amounts of ultraviolet radiation. A single hot O-type star can emit more ultraviolet light than 100,000 Sun-like stars combined. This ultraviolet radiation is critically important because it drives much of the chemistry and physics of the interstellar medium. Ultraviolet photons can ionize atoms, break apart molecules, heat gas, and drive chemical reactions on the surfaces of dust grains. The ultraviolet component of the interstellar radiation field is what creates the H2 regions we discussed earlier, those glowing bubbles of ionized hydrogen around hot young stars. Then there's infrared radiation. As we discussed, interstellar dust grains absorb visible and ultraviolet starlight and re-emit the energy at longer wavelengths in the infrared. This means the entire galaxy glows in the infrared. If you could see infrared light with your eyes, you would see interstellar dust shining everywhere, marking the locations of dense clouds and star-forming regions throughout the galactic disk. About 30 to 50% of all the starlight produced in the Milky Way is absorbed by dust and re-emitted in the infrared. That's a stunning fraction. It means that dust intercepts and reprocesses a huge portion of the galaxy's total light output. The infrared glow of dust is one of the brightest features of the galaxy when viewed at those wavelengths. Radio waves fill interstellar space too. Some come from the 21 centimeter emission of neutral hydrogen atoms that we discussed earlier. Others come from synchrotron radiation produced by cosmic ray electrons spiraling around magnetic field lines. Still others come from molecules in interstellar clouds. Many of the molecules detected in the interstellar medium were found through their radio and microwave emissions. Molecules rotate, and as they change their rotational states, they emit or absorb photons at specific radio and microwave frequencies. By tuning a radio telescope to these specific frequencies, astronomers can detect and identify the molecules present in interstellar clouds. Carbon monoxide, for example, emits strongly at a wavelength of about 2.6 millimeters. Because carbon monoxide is found wherever molecular hydrogen exists, astronomers use carbon monoxide emission as a tracer for molecular gas. It's much easier to detect than molecular hydrogen itself, which emits very weakly at radio wavelengths because of the symmetry of its molecule. And then there's the cosmic microwave background. This is the oldest light in the universe. It was emitted about 380,000 years after the Big Bang, when the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms for the first time. Before that moment, the universe was filled with a hot, dense plasma that was opaque to light. Photons couldn't travel far without being scattered by free electrons. But when neutral atoms formed, the universe suddenly became transparent and the light that had been trapped in the plasma was released. That light has been traveling through space ever since, for about 13.8 billion years. As the universe has expanded, the wavelengths of these photons have been stretched, shifting them from their original visible and infrared wavelengths into the microwave part of the spectrum. Today, this radiation fills all of space uniformly in every direction. It has a temperature of about 2.725 Kelvin, just a few degrees above absolute zero. The cosmic microwave background is the faintest and coldest radiation that fills interstellar space. But it's everywhere. It bathes every dust grain, every gas cloud, every star system in the galaxy with a faint microwave glow that is the remnant echo of the universe's birth. All of these types of radiation combined create the interstellar radiation field, the total electromagnetic energy that permeates the space between the stars. This radiation field isn't just passive background light. It actively shapes the interstellar medium. Ultraviolet radiation ionizes gas and drives chemistry. Infrared radiation from dust carries energy away from dense clouds, allowing them to cool and collapse. Cosmic microwave background radiation sets a temperature floor below which interstellar gas cannot cool. The radiation field is a participant in the physics of interstellar space, not just a byproduct of it. Now, there's something important we need to address about the interstellar medium that changes how you think about it fundamentally. Much of the gas in interstellar space is not neutral, it's plasma. Plasma is a state of matter in which atoms have been stripped of some or all of their electrons, creating a mixture of free electrons and positively charged ions. On Earth, we encounter plasma in lightning bolts, neon signs, and the interior of fusion reactors. But in space, plasma is the most common state of matter. More than 99% of the visible matter in the universe is in the plasma state. Stars are made of plasma. The solar wind is plasma. The gas in H2 regions is plasma. And a significant fraction of the interstellar medium itself is plasma. This matters because plasma behaves very differently from neutral gas. Neutral gas doesn't respond to magnetic fields. The atoms have no net electric charge, so magnetic forces don't affect them directly. But plasma is made of charged particles, ions, and electrons that respond strongly to magnetic fields. In a plasma, the gas and the magnetic field are coupled together. They move together, interact, and influence each other. Astrophysicists describe this by saying the magnetic field is frozen into the plasma. Where the plasma goes, the field goes, and vice versa. This coupling between plasma and magnetic field is fundamental to how the interstellar medium works. It's why the galactic magnetic field can influence the motion of gas on scales of light years. It's why magnetic fields can support molecular clouds against gravitational collapse. It's why cosmic ray particles spiral along field lines rather than traveling in straight lines. The interstellar medium is not just gas and dust in a vacuum. It's a magnetized plasma threaded with energetic particles and bathed in radiation. It's a complex physical system governed by the interplay of gravity, magnetism, thermal pressure, radiation pressure, and cosmic ray pressure. All of these forces and energies come together in a remarkable way at the boundary of our own solar system. Because our sun is not a passive resident of the interstellar medium, it pushes back against it. The sun produces a continuous stream of charged particles called the solar wind. This wind flows outward from the sun in all directions at speeds of about 300 to 800 kilometers per second, carrying with it a magnetic field generated by the sun. The solar wind is a plasma, a stream of protons, electrons, and heavier ions flying outward from the sun into space. As the solar wind flows outward, it inflates a vast bubble in the surrounding interstellar medium. This bubble is called the heliosphere. Inside the heliosphere, the dominant influence is the sun. The solar wind fills the space, the sun's magnetic field pervades it, and the environment is distinctly different from the interstellar medium outside. The heliosphere extends far beyond the orbit of the most distant planets. Its outer boundary, called the heliopause, is roughly 120 to 150 astronomical units from the Sun. 1 astronomical unit is the distance from the Earth to the Sun, about 150 million kilometers. So the heliopause is about 18 to 22 billion kilometers from the Sun. That's an enormous bubble. It extends about 3 to 4 times farther from the Sun than Pluto's orbit. Everything inside this bubble, every planet, every moon, every asteroid, every spacecraft we've ever launched, exists within the protective cocoon of the heliosphere, shielded from the full brunt of the interstellar medium by the outward pressure of the solar wind. The heliosphere protects us. The interstellar medium outside the heliosphere contains cosmic rays, interstellar gas, interstellar dust, and galactic magnetic fields. The solar wind and the sun's magnetic field deflect many of the lower energy cosmic rays that would otherwise bombard Earth directly, perhaps reducing the flux several times over for the lower energy particles. The increased radiation without this shielding could damage DNA, increase mutation rates, and potentially make the surface of the planet more hazardous for life. The heliosphere is one of several protective layers that make life on Earth possible, alongside Earth's own magnetic field and atmosphere. In 2012, something extraordinary happened. Voyager 1, the spacecraft launched by NASA in 1977, crossed the heliopause and entered interstellar space. For the first time in human history, a human-made object was sampling the interstellar medium directly. Voyager 1 detected a dramatic change in conditions as it crossed the boundary. The density of charged particles from the solar wind dropped sharply. The density of cosmic rays, high-energy particles from outside the solar system, increased. The magnetic field changed direction, shifting from the orientation imposed by the sun to the orientation of the local interstellar magnetic field. Voyager 1 also measured the density of the interstellar plasma directly using its plasma wave instrument. When a coronal mass ejection from the Sun reached the heliopause region, it caused the interstellar plasma to vibrate, producing oscillations that Voyager's instruments could detect. From the frequency of these oscillations, scientists calculated that the density of the interstellar medium just outside the heliosphere is about 80,000 electrons per cubic meter. That's roughly 0.08 electrons per cubic centimeter. Thin almost beyond imagination, but real, measurable. A physical environment with definite properties. Voyager 2 crossed the heliopause in 2018, providing a second measurement at a different location. Its readings confirmed and complemented Voyager 1's findings, showing that the heliopause is a real physical boundary where the solar wind gives way to the interstellar medium. The two spacecraft are now both traveling through interstellar space, moving outward at about 17 kilometers per second for Voyager 1 and about 15 kilometers per second for Voyager 2. They are our first direct ambassadors to the space between the stars. They're sampling the interstellar medium as they go, measuring its density, temperature, magnetic field, and cosmic ray environment. Their instruments are aging, their power sources are slowly fading, and by the mid-2030s, they'll likely go silent, unable to power their transmitters any longer. But for now, they continue to send data back to Earth from beyond the edge of the Sun's influence, from the true space between the stars. What Voyager has taught us is that interstellar space is not abstract. It's not theoretical. It's a place, a physical environment with measurable properties. It has a density. It has a temperature. It has a magnetic field with a specific strength and direction. It has cosmic rays passing through it. It has radiation bathing it from all directions. It's a real environment, as real as the air in your room, just incomparably thinner and vastly larger. The space between the stars is filled with matter and energy and forces that interact in complex ways. And those interactions determine the structure and evolution of the galaxy itself. The magnetic fields guide the movement of gas and charged particles. The cosmic rays ionize and heat the deep interiors of molecular clouds. The radiation field drives chemistry and controls temperatures. The plasma state of much of the gas couples it to the magnetic field, creating a system where matter, energy, and forces are inseparably intertwined. None of these components exist in isolation. They're all connected, all part of a single dynamic environment that fills the vast darkness between the stars. And understanding this environment, understanding all of its invisible layers, is essential to understanding why the galaxy looks the way it does, why stars form where they do, and ultimately why planets like Earth exist at all. Now, here's something that might surprise you. We've been talking about the interstellar medium as though it's one thing. A thin soup of gas and dust spread between the stars. But it's not one thing. It's many things. The interstellar medium exists in several completely different physical states, simultaneously, occupying different regions of space, coexisting side by side, interacting at their boundaries. Astronomers call these states phases. And understanding these phases is the key to understanding the true hidden structure of interstellar space. Think of water. On Earth, water exists in three phases: ice, liquid, and steam. All three are the same substance, but they behave completely differently depending on temperature and pressure. All three phases can exist simultaneously. You can have ice floating in liquid water with steam rising from a hot spring nearby. The same substance in three different states, occupying different regions of the same environment. The interstellar medium works in a similar way, except instead of three phases, astronomers have identified at least 5 major phases, and the temperatures involved range from just a few degrees above absolute zero to millions of degrees. The differences between these phases are far more extreme than anything you encounter with water on Earth. The coldest phase of the interstellar medium is the molecular gas found in molecular clouds. We talked about this earlier. These are the dense, dark, frigid regions where hydrogen exists as molecules rather than individual atoms. Temperatures in molecular clouds range from about 10 to 20 Kelvin. That's minus 250 to minus 260 degrees Celsius. These are some of the coldest places in the entire universe. Colder than the surface of Pluto, colder than the dark side of the moon, almost as cold as it's physically possible to be. The densities in molecular clouds, while still incredibly low by earthly standards, are the highest found anywhere in the interstellar medium, ranging from a few hundred to more than 1 million molecules per cubic centimeter in the densest cores. Molecular clouds occupy a relatively small fraction of the total volume of the interstellar medium, maybe 1 to 2%. But because they're so much denser than everything else, they contain a significant fraction of the total mass, perhaps 30 to 40% of all the gas in the galaxy. The next phase is the cold neutral medium. This is atomic hydrogen gas at temperatures of about 50 to 100 Kelvin, roughly minus 220 to minus 170 degrees Celsius. It's warmer than molecular clouds, but still frigidly cold. The density is lower than in molecular clouds, typically around 20 to 50 atoms per cubic centimeter. The cold neutral medium exists in sheets, filaments, and clumps throughout the galactic disk. It occupies maybe 1 to 5% of the volume of the interstellar medium. This phase is essentially the outer layer surrounding molecular clouds. Gas in the cold neutral medium can transition into molecular gas if it gets compressed or shielded from radiation, and molecular gas can transition back into the cold neutral medium if a nearby star heats it, or if the cloud disperses. Then there's the warm neutral medium. This is atomic hydrogen at much higher temperatures, roughly 6,000 to 10,000 Kelvin. That might sound hot, and by everyday standards it is. But remember, the gas is incredibly thin. A few tenths of an atom per cubic centimeter. You could pass through this gas and never feel any warmth at all because there are simply too few particles to transfer any meaningful amount of heat to you. The warm, neutral medium fills a substantial fraction of the galactic disk, perhaps 30 to 40% of its volume. It's the background gas that fills much of the space between the denser clouds. This is the phase of the interstellar medium that produces much of the 21 centimeter radio emission that astronomers use to map neutral hydrogen across the galaxy. Alongside the warm neutral medium exists the warm ionized medium. This phase has similar temperatures, roughly 8,000 Kelvin, but the hydrogen is ionized rather than neutral. The electrons are being stripped from the atoms by ultraviolet radiation from distant hot stars. The density is very low, around 0.2 to 0.5 electrons per cubic centimeter. The warm ionized medium is widespread throughout the galaxy. It fills roughly another 20 to 30% of the galactic disk's volume. It's detected through the faint glow it produces as electrons recombine with protons, and through its effect on radio signals from distant pulsars. When a radio pulse from a pulsar travels through the warm ionized medium, the free electrons in the plasma slow down the lower frequency components of the pulse slightly more than the higher frequency components. This dispersion of the pulse tells astronomers how many free electrons are along the line of sight, allowing them to map the distribution of the warm ionized medium across the galaxy. And finally, there's the hot ionized medium. This is the most extreme phase of the interstellar medium. Temperatures range from about 100,000 to several million Kelvin. The gas is so hot that every atom is completely stripped of its electrons. It's a fully ionized plasma at temperatures comparable to the interior of the sun's outer atmosphere. But the density is fantastically low, about 0.003 to 0.01 atoms per cubic centimeter. To put that in perspective, if you scooped up a cubic meter of this gas, you capture maybe a few thousand particles. Compared to a cubic meter of air on Earth, with its roughly 25 trillion molecules, this is essentially nothing. This is the thinnest, most rarefied phase of the interstellar medium. There is almost nothing there, and yet it fills an enormous volume. The hot ionized medium occupies roughly 40 to 70% of the total volume of the interstellar medium. It's the dominant phase by volume. Most of the space between the stars, if you measure by volume rather than by mass, is filled with this searingly hot but almost immeasurably thin plasma. How can gas in interstellar space be millions of degrees? The answer is supernovae. When a massive star explodes, it releases an almost incomprehensible amount of energy. A single supernova can briefly outshine an entire galaxy of hundreds of billions of stars. Most of that energy goes into the kinetic energy of the expanding debris and the neutrinos produced in the core collapse. But a significant fraction goes into heating the surrounding interstellar medium. The blast wave expands outward at thousands of kilometers per second, slamming into the surrounding interstellar gas. The shock wave compresses and heats the gas it encounters to temperatures of millions of degrees. Think about what's happening here. The shock wave is moving so fast that when it hits interstellar gas, the atoms in that gas are suddenly accelerated to enormous speeds. Temperature is really just a measure of how fast particles are moving. When you slam atoms with a shock wave moving at 5,000 kilometers per second, you heat those atoms to millions of degrees almost instantly. The expanding shell of superheated gas sweeps up the surrounding material, pushing it outward and leaving behind a cavity filled with hot, low-density plasma. This cavity is called a supernova remnant. Over time, hundreds of thousands of years, the remnant expands, cools, and eventually merges with the surrounding interstellar medium. But while it's expanding, it creates a hot bubble in the galactic disk. And because massive stars tend to form in clusters and associations, multiple supernovae often go off in the same region within a few million years of each other. Each explosion reinforces the hot bubble before the previous one has had time to cool. The result is a superbubble, an enormous cavity of hot gas carved out by the combined action of multiple supernovae and strong stellar winds from massive stars. Superbubbles can be hundreds of light years across and can persist for millions of years. And here's something remarkable. We live inside one of these superbubbles. It's called the local bubble. The local bubble is a cavity of hot, low-density gas surrounding our solar system. It stretches roughly 1,000 light years across in its widest dimension. though its shape is irregular, elongated more in some directions than others. Inside the local bubble, the density of the interstellar medium is roughly 100 times lower than the average density of the galactic disk. The gas is hot, roughly 1,000,000 Kelvin, and it emits faint X-rays that have been detected by space-based X-ray telescopes. The local bubble was carved out by a series of supernova explosions that occurred in our cosmic neighborhood over the past 10 to 20 million years. Astronomers have traced the history of these explosions by studying the ages and motions of nearby stellar associations, groups of stars that form together and are now drifting apart. The evidence points to roughly 15 to 20 supernovae that exploded in the general vicinity of where the Sun is now over the past 20 million years. Each explosion sent a shock wave through the surrounding interstellar medium, heating the gas and pushing it outward. Over millions of years, these repeated explosions hollowed out the cavity we now inhabit. The walls of the local bubble, where the swept-up gas has accumulated, are denser than the interior. And something fascinating has been discovered about those walls. In a study published in 2022, astronomers used three-dimensional maps of nearby molecular clouds created using data from the European Space Agency's Gaia spacecraft, and showed that essentially every major star-forming molecular cloud within about 500 light-years of the Sun sits on the surface of the local bubble. The Taurus molecular cloud, the Ophiuchus cloud complex, the Chameleon clouds, the Lupus clouds, all of them are located on the bubble's expanding shell. This means the same supernovae that carved out the local bubble also compressed the gas at its edges into the very clouds that are now forming new stars. Star death created the conditions for star birth. The supernovae that hollowed out our cosmic neighborhood simultaneously triggered the next generation of star formation in the surrounding walls. The evidence for the local bubble comes from multiple observations. First, when astronomers measure the amount of neutral hydrogen between the Sun and nearby stars, they find very little. Stars within about 500 light-years of us show far less interstellar absorption than you'd expect based on the average density of the galactic disk. Something has cleared out the gas in our neighborhood. Second, space-based X-ray telescopes detect a faint diffuse glow of soft X-rays coming from all directions. This emission is consistent with hot gas at about 1,000,000 Kelvin filling a large volume around the Sun. Third, the distribution of interstellar sodium, which can be measured through absorption lines in starlight, shows a clear deficit in our neighborhood, consistent with a low-density cavity. The local bubble isn't unique. There are other similar bubbles nearby. The Loop 1 superbubble, associated with the Scorpius-Centaurus stellar association, lies adjacent to the local bubble. These two bubbles appear to be interacting, with their walls merging or overlapping in some regions. Farther away, there are other superbubbles scattered throughout the galactic disk, each one carved out by supernovae from stellar clusters. The galactic disk is riddled with these cavities, like Swiss cheese. Hot, low-density bubbles are surrounded by denser walls of swept-up gas. Where bubbles collide, the compressed walls between them become particularly dense, sometimes dense enough to become gravitationally unstable. And in these dense, compressed regions, new molecular clouds can form. New stars can be born. The deaths of one generation of stars literally create the conditions for the birth of the next. The cycle continues, driven by gravity and thermonuclear fire, sustained by the interstellar medium. This brings us to one of the most profound aspects of the interstellar medium. It's not static. It's not a fixed background. It's a dynamic, evolving, constantly changing environment. And the force that drives most of this change is the life cycle of stars. Stars form from the interstellar medium. They spend millions or billions of years burning nuclear fuel in their cores. And when they die, they return material to the interstellar medium, enriched with heavy elements that were forged in their interiors. This is the galactic recycling process, and it connects every star in the galaxy to every other star through the shared material of the interstellar medium. Here's how it works. A molecular cloud collapses under gravity and forms a cluster of new stars. The most massive stars in that cluster are the first to die. They live fast and die young. A star with 25 times the mass of the Sun might live only about 7 million years before it exhausts its fuel. In its final moments, the star explodes as a supernova, blasting its outer layers into space at speeds of thousands of kilometers per second. This debris contains elements that were synthesized in the star's core during its lifetime. Carbon, forged by the fusion of helium. Oxygen, produced when carbon captures another helium nucleus. Silicon, sulfur, calcium, and iron, produced in the final stages of nuclear burning. And elements heavier than iron, like gold, platinum, and uranium, produced in the supernova explosion itself or in neutron star mergers. All of these elements are scattered into the interstellar medium, mixing with the existing gas and dust. Meanwhile, smaller stars in the same cluster are still burning hydrogen peacefully. They'll live for billions of years. But eventually, they too will die, each in its own way. Stars like the Sun will swell into red giants, shed their outer layers as planetary nebulae, and leave behind white dwarf remnants. The shed material, enriched with carbon and nitrogen from the star's interior, returns to the interstellar medium. The white dwarf remnant cools slowly over billions of years, effectively removing mass from the cycle permanently, at least on any timescale that matters for the galaxy's evolution. The material returned to the interstellar medium by dying stars doesn't just sit there. It mixes with the existing gas. It gets swept up by supernova shockwaves. It gets compressed in spiral arm passages. Eventually, it ends up in a new molecular cloud. And within that cloud, the enriched gas collapses to form a new generation of stars and planets. These new stars contain a slightly higher proportion of heavy elements than the previous generation because each cycle of starbirth and death adds a little more heavy material to the interstellar reservoir. This process has been going on for billions of years. The Milky Way has been forming stars for roughly 13 billion years, since shortly after the Big Bang. The first generation of stars formed from gas that was almost pure hydrogen and helium, the primordial material created in the Big Bang. Those stars lived, died, and returned enriched material to the interstellar medium. The second generation formed from slightly enriched gas and returned even more heavy elements when they died. Each successive generation was born from gas that was a little richer in heavy elements than the one before. Our Sun is roughly a third generation star. The gas from which it formed, about 4.6 billion years ago, had already been through at least 2 previous cycles of starbirth and death. The heavy elements in the solar nebula, the elements that would eventually become Earth and everything on it, were produced by earlier generations of stars that lived and died before the Sun existed. Astronomers can tell this because the Sun contains about 1.4% heavy elements by mass. That might not sound like much, but it's far more than the universe started with. The primordial gas from the Big Bang was essentially 0% heavy elements. Every atom of carbon, oxygen, silicon, and iron in the Sun was manufactured inside previous generations of stars and cycled through the interstellar medium before being incorporated into the cloud that collapsed to form our solar system. This means the interstellar medium is not just the raw material of the galaxy. It's the memory of the galaxy. It carries within it the accumulated chemical legacy of billions of years of stellar evolution. Every atom of carbon in your body was once inside a star. It was fused from helium in the core of a red giant, expelled into interstellar space when that star died, drifted through the darkness for millions of years, was incorporated into a new molecular cloud, and eventually became part of the solar system, and ultimately part of you. The same is true of the oxygen you breathe, the iron in your blood, the calcium in your bones. All of it passed through the interstellar medium. All of it was processed through the life cycle of stars. You are, in the most literal physical sense, made of interstellar material. And this recycling process is still happening right now. Right now, in molecular clouds throughout the Milky Way, new stars are forming from gas that has been enriched by previous generations of dying stars. Right now, massive stars somewhere in the galaxy are exploding as supernovae, seeding the interstellar medium with freshly forged heavy elements. Right now, red giant stars are shedding their outer layers, returning carbon and nitrogen to the interstellar reservoir. The interstellar medium is alive with this process. It's not the empty dead void it appears to be when you look up at the night sky. It's the active circulatory system of the galaxy, carrying material from dying stars to new ones in an endless cycle of creation and destruction that has been running since the galaxy was young. The interstellar medium also shapes the galaxy on the largest scales. The distribution of gas in the galactic disk determines where new stars can form, which in turn determines the brightness and structure of the spiral arms. The magnetic field threading through the interstellar medium influences the flow of gas and the propagation of cosmic rays, affecting the dynamics of the entire disk. Supernova-driven bubbles and superbubbles stir the gas, creating turbulence that mixes elements throughout the disk and prevents the gas from settling into a perfectly smooth distribution. The interstellar medium is what makes the Milky Way a living galaxy, one that's still evolving, still changing, still producing new stars and planets. Without the interstellar medium, the Milky Way would be dead. It would consist entirely of aging stars slowly burning through their fuel with no possibility of renewal. No new stars, no new planets, no possibility for new life. Eventually every star would burn out and the galaxy would go dark. The interstellar medium prevents this. By providing a reservoir of raw material that's constantly being recycled and replenished, it keeps the galaxy alive, generation after generation. So let's return to where we started. You go outside on a clear night and look up. You see stars, and between the stars, you see darkness. And for most of your life, you probably assumed the darkness was empty. Nothing. A void. But now you know better. That darkness is filled with hydrogen gas in multiple phases. Atomic hydrogen drifting at thousands of degrees. Molecular hydrogen huddled in frigid clouds at just a few degrees above absolute zero. ionized hydrogen glowing faintly around hot young stars. That darkness contains microscopic dust grains, silicate minerals and carbon compounds, and tiny ice-covered particles, each one smaller than a wavelength of visible light, absorbing and reddening the starlight that passes through them. That darkness is threaded with magnetic fields stretching across the galaxy, weak at any single point but powerful across light years, guiding the motion of charged particles and regulating the collapse of clouds into new stars. That darkness is filled with cosmic rays, individual protons, and atomic nuclei traveling at nearly the speed of light, accelerated by the shock waves of ancient supernovae, streaming through the galaxy in every direction, ionizing molecules in the heart of dark clouds and influencing the chemistry of star-forming regions. That darkness is bathed in radiation, starlight, infrared glow from warm dust, ultraviolet radiation from hot, massive stars, radio waves from spiraling electrons and rotating molecules, and the cosmic microwave background, the faint remnant glow of the Big Bang itself, filling every corner of space with a whisper of light that has been traveling for 13.8 billion years. That darkness is structured. It has phases and regions and boundaries. Hot bubbles carved by supernovae sit beside cold, dense clouds on the verge of collapsing into new stars. Warm, diffuse gas fills the spaces between. The interstellar medium is layered, textured, and organized. Not random, not uniform, not featureless. It has architecture, and you're sitting inside one of its structures right now. The local bubble, a cavity of hot, thin gas hollowed out by supernovae that exploded millions of years before humans existed, surrounds our solar system. Every night when you look at the sky, you're looking out from inside a structure of the interstellar medium, and that darkness is alive with change. Stars are being born from it. Stars are dying and returning material to it. Shock waves are compressing it, heating it, stirring it. Magnetic fields are threading through it, guiding its flows. Cosmic rays are ionizing it and depositing energy into its coldest regions. The interstellar medium is not a backdrop. It's not a stage. It's a participant. An active, dynamic, essential component of the galaxy that connects every star to every other star through the shared material from which they all formed and to which they all return. The space between the stars is not empty. It has never been empty. It is the hidden ocean in which the stars are islands. It is the reservoir from which new worlds are drawn and to which old worlds eventually return. It is the medium through which the galaxy breathes, recycles, and renews itself across billions of years. And every atom in your body, every element heavier than hydrogen and helium that makes up the planet beneath your feet, the air in your lungs, the water in your cells, all of it passed through this medium. All of it drifted through the darkness between the stars, carried in the thin, cold gas, dusted onto microscopic grains, swept through supernova remnants, compressed in molecular clouds, before finally coming together to form the solar system, and ultimately to form you. You are not separate from the interstellar medium. You are made of it. Every breath you take contains atoms that were once drifting between the stars. The iron in your blood was produced in the final seconds of a supernova explosion, flung into the darkness, and eventually recycled into the molecular cloud that became our solar system. So the next time you look up at the night sky, don't just see the stars. See what's between them. See the invisible ocean of gas and dust and fields and energy that fills the darkness. See the cold clouds where new stars are being born right now. See the hot bubbles carved by ancient supernovae, the same kind of bubble that surrounds you right now. The space between the stars is not nothing, it's everything. It's the raw material of the universe made visible not through light, but through understanding. It's the medium that connects every star in the galaxy to every other star. The substance from which worlds are made. The environment in which the galaxy lives and breathes and evolves. And you are part of it, made from it, sustained by it, connected to it across 4.6 billion years of cosmic history. The darkness between the stars is not empty, it is full, it is rich. It is the most important substance in the galaxy. And now you know what's actually out there, hiding in the vast quiet spaces between the stars. Thank you for joining me on this journey. If you found this exploration valuable, a like or subscribe would mean a lot. It helps me keep making these deep dives into the cosmos. Good night. And remember, the next time you look up and see darkness between the stars, you're not seeing nothing. You're seeing everything that makes the galaxy alive.